Back a few years ago, the television show Mythbusters had a special episode on superheroes, and it focused on technologies that you find in superhero movies and superhero comics, and asked whether these things are physically possible or even plausible. And one of those features is particularly relevant to some of the dynamics topics that we've been talking about recently. So I'll let the narrator of the television show describe what it is.
We're flying high in a superhero special, and the next myth combines cars and comic book craziness.
Next up, Batmobile 90-degree turn.
Batman, to get away from the bad guys, screaming down the street, and to escape, all he has to do is push a button that deploys a grappling hook, grabs onto a steel structure, and it whirls him around the corner. And the crooks can't get him.
Awesomeness, Grant Man. Let's see how this myth works. During our comic strip car chase, our hero hits a button, and a grappling hook fires from the car, wraps himself around a steel structure, and swings our superheroes through a high-speed 90-degree turn to safety. Here's the plan. The guys will mount an air-powered cannon in a car, fire a grappling hook at speed, and see if the cable can swing the car around a right-angle bend.
So on the show, one of the guys on the Mythbusters team gave us a summary of his analysis. I'll let you listen to it.
Path. Once we hook onto that structure into a circular one. Now, this induces a force that points inwards towards the center called centripetal force. And you can calculate that based on the weight of the car, the distance from the center, and the speed that you're going. I've run the numbers, and we should be experiencing about 7,000 pounds, and that's going to be the tension on the cable. So we're going to select our cable to be more than adequate to handle that amount of force.
So what I'd like to do first is to perform a quick but more thorough analysis of what he just said. First thing is the mass of the car. You'll see a little later on that the car they use is a 1980s Camaro, which is about 3,000 pounds. And again, I want mass. 3,000 pounds is a weight. It's a force. So to get a mass, I divide by G, 32.2 feet per second squared. I get 93.17 pounds seconds squared per foot. There's another name for this, of course. It's called a slug, if you're interested. Another parameter of the problem they have is that they're going to drive their car at a velocity of 30 miles per hour. Now, since I already have my mass in terms of feet and second, to make the units consistent, it's probably best if we turn this into feet per second rather than miles per hour. So in order to do that, all I have to do is multiply by 5,280 feet per mile. Notice that the miles will cancel out in that case. And then also multiply by 1 hour per 3,600 seconds. So this is mile per hour, so the hour here would be in the denominator. That cancels out. And what we're left with is something in feet and second. And if you work out the arithmetic, this ends up being 44 feet per second. So if we're going to do any analysis, it makes sense to draw a free body diagram, forces on the body. I've got a force towards the center. I presume it's primarily provided by the cable. It could also be provided by the tires on the car. But nonetheless, this is a force. On my free body diagram here, I have a force inward. And I'm going to call that inward force T, because I suspect that'll be primarily due to the tension in the cable. So T in the positive E hat 2 direction. I'm going to assume that we're not applying the brakes during the turn. We're not stepping on the gas pedal either. So there'll be no forces in the longitudinal direction. Nothing speeding up or slowing down the car. Now for mass acceleration diagram, again we're going at a constant speed, so the only acceleration we get is that due to centripetal acceleration. And this is going to be m times speed squared divided by a radius of curvature. I'm calling that r. And of course that's in the E hat 2 direction as well. So now we'll apply Newton's second law in the E hat 2 direction, that direction perpendicular to the path. What I have is a tension pulling inward, and this has to equal mass speed squared divided by radius. And lo and behold, I have an expression for tension in terms of mass, speed, and radius, just like the guy in the television show said there should be. Now, looking at the terms in this equation, you might recall that the person gave us the tension that he's expecting in the cable, right? And that cable tension was about 7,000 pounds, I recall. And presumably that would include the tire force too, but 7,000 pounds we're after. And we're given mass, and we're given speed, right? So the only thing we're not giving in this equation is radius. So what this analysis allows us to do is estimate the radius at which they're driving this car, because they never really tell us that. So we can get it from other information that he gave us. So if you take this and solve it for r instead of t, you get this expression right here, and of course we can start substituting our numbers in. And what I find is that if all these numbers are correct, I've got a radius of about 26 feet. Again, we got it without them telling us what that radius is, but 26 feet is what I've got. So just to round things off and perhaps make a slightly more conservative estimate, I'm going to, instead of taking 26 feet here, I'm going to just make this an easy 30. So for the rest of the video, we'll assume that the radius of this turn, 30 feet. Now before we move on, I'd like to make one observation. That is, the tires on this vehicle have a coefficient of static friction of about 1. What this tells us is that the maximum friction force that these tires can produce is about 1 times the normal force on the tires. So it can produce at most about 3,000 pounds of sideways force. But to go around this turn requires 7,000 pounds of force, which means that most of this force T right here must come from the cable tension. It can't come from the tires because tires can produce at most 3,000 pounds. Therefore, the cable's doing the bulk of the pulling to go around the turn. Now, on the television show, the crew built this rather remarkable air cannon for shooting this big steel grappling hook. And attached to that grappling hook was a rope. Presumably, it was strong enough to hold that 7,000 pounds of force necessary to bring the car around the turn, perhaps more than the 7,000 pounds of force, as was promised. And let's check out how the experiment went. So here's the car cruising at 30 miles per hour, and it's approaching the turn. As soon as they change the camera angle, you can see that steel structure they're going to try to latch onto. There goes the cannon, and it goes around the turn, and what exactly is happening here? Well, in a second you'll see a slow motion of this hook. Remarkably, it just latched right on beautifully, but look, you see the rope just snapped right off? Now here's another look at that hook latching on. Look at this thing. It grabs on, pow, you can see that rope just fly right off. So if you look at the rope, as we will in just a second, you'll see that this thing just frayed. It just shredded into little pieces. And what happened to this rope that was supposed to hold the 7,000 pounds? Now, because of this failure, the team decided to go to a braided steel cable. This one was capable of holding 15,000 pounds. Surely that would be enough, right? So they ran the experiment again. Here it is approaching. It launched the cannon, and oh, doesn't look good, does it? Let's look at the slow motion again. Here it is. The hook comes out, latches on beautifully, but then the cable snaps like a cheap fishing line, right? It was not strong enough, not even close.
It broke not once, but twice, at the hook and the car. Despite its immense braking strength, it snapped as if it were cotton twine.
This is where the hook was connected to the cable, and it totally shredded. I mean, it's just not strong enough. This cable is not strong enough. This one's looking busted.
This myth needs a cable that just doesn't exist. One that's lightweight so it can be fired, flexible so that it can wrap, yet immensely strong to withstand the massive force.
So the Mythbusters crew concluded, based upon these few experiments that they ran, that the grappling hook idea for swinging the car around a turn is completely impossible. Well, if you're an engineer, you should think of this as a cop-out, right? You should be completely dissatisfied with this answer. Remember, if we go back to the analysis, we found that if we have a 3,000-pound car going around at 30 miles per hour, a radius of 26, 30 feet, then it should only take about 7,000 pounds of force to do this, right? Why was a 15,000-pound cable insufficient to make this work? So to me, it seems like the best way to explain what happened in this problem is to look at the video almost frame by frame as this thing's going along. So here you can see it going forward and backing up. But here we see that hook being shot out, and there's the cable. That's the hook itself, right? And you can see it moving with the car because it's shot from a moving car, which is kind of really cool to see. But here's where it grabs, or here's where it at least first touches that steel structure right there. When it first comes into contact with the steel structure, notice the car is even with the steel structure, right? Now here's another view of the hook coming in contact with the structure. There's the hook right there, and you see the cable attached to it. The car's off to the side, out of frame at this moment. And let me advance this thing almost frame by frame. As it comes in, notice that it doesn't latch onto the structure immediately. In fact, you can come back up and bring it back in. You can see it sort of clang right into the side of it, right? It bounces right off it, but it goes right inside the thing, bounces around inside some more. It looks as though it might be latching on. No, I see it's tumbling. See the hook tumbling around inside there still? And meanwhile, the car is just coming into frame now, while the hook is still bouncing around inside. Notice that the cable is still slack. You can see this thing almost flapping in the breeze. So it's bouncing around in there, bouncing around some more. Ooh, here's where the hook finally engages. You can almost see the structure start to bend a little bit. And let's watch it some more. And wow, now you can see it go. Ooh, do you see the thing snap right there? So, ooh, right there's where it snapped. Right here's where it's engaged. And it's just 1 or 2 frames where you can see the rope or the cable just start to tension up and then finally break. Here, just this part right here just turned to dust, it looks like, as the cable broke, right? So that's how the mechanics of that thing work. But most important is that while the cable was bouncing around in there, the car was still traveling forward. The car may have traveled a full car length, maybe even 2 car lengths forward, while that hook was bouncing around inside that cage. So when we originally conceptualized the path that the car would take, it looked something like this, right? The car would enter this turn, it would launch the grappling hook, and by the time it reached the beginning of the turn, the grappling hook would be in place, and that would pull the car around this perfectly circular arc that we have shown here. But in the actual experiments, the path looked more like this. That is, the car entered what was supposed to be the beginning of the turn, a distance r away from that steel structure. R was about 30 feet, you recall. But the cable did not become tight until the car had traveled a good distance d later, where distance was maybe almost a car length later on. So at that time, the cable became tight. And if the cable did not break, the cable would have snapped the car around the circular arc like so. So in the rest of this analysis, I'm going to assume that the cable did not break. And we'll see what sort of forces would be necessary if the cable were not to break. Again, remember the car travels straight for a little while, then the cable becomes tight, and then the car goes around this circular arc right here. Now in analyzing this problem, I'm going to look at the instant just before the rope becomes tight and just after the cable becomes tight. Remember, this is the critical time. This is the time in which the rope snapped in their experiments. Again, I'm going to assume that the rope does not snap and see what is required for this rope to remain intact. For this analysis, I will consider 2 sets of coordinates. One is your standard I hat, J hat coordinates, which the J hat is aligned with the initial velocity coming into the turn. And the other coordinates I'll use are E hat 1 and E hat 2. This is a direction tangent to the path and a direction perpendicular to the path right here, pointing inward. If I were to draw a free body diagram for this car, it doesn't really look like a car there, but it would look something like this. There's the car. The only real significant force in this problem is that one due to the cable tension. The cable tension is radially inward. So that right there is my free body diagram. So to study this problem, I propose we use the angular impulse, angular momentum principle. And what we're going to do is take moments about point P, which is this point down here where we're attaching about. I'm going to say that the angular momentum about point P at some time I'll call TA, this is the time just before the string becomes tight, plus the angular impulse, this is an integral from TA to TB of the moment about point P. I'm integrating with respect to time. This has to equal the angular momentum about point P after the cable becomes tight. And the nice thing about this can be seen if we look at this moment, right? Remember the force of significance in this problem is the tension in the cable, and the tension is acting through point P. So therefore this tension in the cable does not create a moment about point P. And so very conveniently, this term goes away. The integral isn't there. And what I have is the angular momentum before the rope becomes tight is equal to the angular momentum after the rope becomes tight. Very nice. So let's start with time TA. Just before the rope becomes tight, the velocity of the car is in the J hat direction, right? So there's my velocity. Let me call it VA, which is a speed of 30 miles per hour in the J hat direction. There's my initial velocity. So remember the equation for angular momentum, say about point P, is going to be r, this is position vector r, cross linear momentum m times v. Here position vector r means a vector starting at point P and extending to where the particle is, or in this case the car is, and that would be position vector r right there. So I'm taking a vector cross product of this vector, this pink vector, times that yellow velocity vector. It's the perpendicular distance that's going to matter here, right? So I've got r, capital R, this distance r, the 30 feet if you like, times m times speed at a, and this vector cross product is going to be a vector in the minus k hat direction right there. So there's my angular momentum before the rope becomes tight. All right, now let's think about angular momentum after the rope becomes tight. After the rope becomes tight, the car is moving in this direction. It's moving tangent to the circle. So I'll say the velocity at time instant b, I'll call it vb, and that will be in the e hat 1 direction. So now the angular momentum after the rope becomes tight, that's this guy right here, I got to put an equal sign. Again, it's the vector cross product with this pink vector r with that velocity vector vb, and notice that this time I have a right angle between these two things. So this is going to be this distance right here, which is, what is that? I can use Pythagorean theorem to find the distance, right? So that's going to be r squared plus d squared square root times vb, and that has to be in the minus k hat direction too. Aha, so these two angular momenta have to equal each other, which tells us that speed after the rope becomes tight is equal to, both sides have a minus sign, I can cancel out, both sides have a mass. Oops, one side doesn't have a mass. There's supposed to be a mass in here. There we go, now it has a mass. I mean to squeeze it in. So now I'm solving for VB again, right? So this is going to be r divided by r squared plus d squared square root times VA. So let me just rewrite this result over here, but in vector form. So the velocity of the car after the rope becomes tight is going to be given by this, right? There's the speed itself, but the velocity is all in the e hat 1 direction. So let me put that on there, because I'm going to use that again in just a minute. But before I do, let me make an observation. Remember we said that this capital R, the thing that was going to be the radius of our curve here, that we said was about 30 feet. And this D, we said it was more or less a car length. A car length for the IROC Camaro was about 16 feet. Let's just keep this conservative. Let's say D is about 12 feet. In that case, if I use these numbers, then this quantity right here, this little ratio that appears in front of the VA, what is that? That's, if you put those numbers in, I get 0.928. So in other words, the cable becomes tight. The car is losing a little over 7% of its speed. And if you take 0.928 and you square that, you get 0.861, which means that it would be losing about 14% of its kinetic energy as that rope becomes tight. So what's happening with that speed? Or what's happening with that kinetic energy? Can you explain where it went? So to explain where that velocity went, what happened to it, I'm going to take a slightly different perspective on this problem. What I'd like to do is look at the velocity vector at instant A again. This is the velocity vector just before the rope becomes tight. And what I'd like to do is decompose this velocity vector into components in the e hat 1 and the e hat 2 directions. Just follow me for a moment if this doesn't seem rational yet. So VA here has a component tangent to the circular arc that goes this way, and a piece perpendicular to the circular arc which goes that way, which I'll draw right over here. Now if I call this angle right there theta, then velocity before the rope becomes tight is going to be a VA cosine of theta in the e hat 1 direction. Then I'll have a minus VA, it's going to be sine theta in the e hat 2 direction. And it's a minus there because the positive e hat 2 direction is that way and this component of velocity is the other way. And now the next thing I'll observe is that this angle theta right here is the exact same thing as that angle theta right there. Ooh, those triangles are congruent, which means that cosine of phi is just r divided by this hypotenuse, right? And likewise, instead of a sign right here, I could write this as d divided by the hypotenuse. And now I'm hoping you see something, right? Look at this velocity VA. I've split it into E hat 1 and E hat 2 component. And look at this velocity VB. This is after the string becomes tight. Notice something? This E hat 1 component of VA is the same as the E hat 1 component of VB, right? In other words, this E hat 1 component of the velocity is preserved when the cable becomes tight. Nothing changes in the E hat 1 direction. What changes is what happens in the E hat 2 direction, right? I initially have a velocity in the E hat 2 direction. That's the direction perpendicular to the circular arc. It's the direction in the same direction as my tension. And what happens is my tension very abruptly kills this E hat 2 component of velocity. Before the rope becomes tight, I have both components of velocity. After the rope becomes tight, this part of the velocity goes away. That part survives. Very interesting, isn't it? So that's what happened to my velocity. That's what happened to my kinetic energy. It's this part that just suddenly disappeared when that rope became tight. So what I would like to do is bring up the linear impulse momentum principle. The linear impulse momentum principle says you take your linear momentum before the rope becomes tight plus this impulse right here. The impulse is the time integral of my tension. This has to equal the linear momentum after the rope becomes tight. This time I can't get rid of this impulse, right? There's no way that the integral of this thing is 0. But what I want to do is look at the E hat 2 component of that linear impulse momentum principle. Just before the rope becomes tight, the E hat 2 component of velocity is this one right here. So I've got a minus d over r squared plus d squared, square root VA, like so. So there's my initial momentum, my E hat 2 component of momentum going into this situation just before the rope becomes tight. Plus, again, here's the impulse. And this has to equal what? It's the E hat 2 component of momentum after the rope becomes tight. But there is no momentum in the E hat 2 direction, so this has to equal 0. So to explain what's going on here, let's start looking at some numbers. First, I want to pull off this little piece right here. M times VA. This is the initial momentum of the car before the cable gets tight. The mass of this thing, this is a 3,000 pound car. Let's take 3,000 divided by 32.2 to get the actual mass, but you get the idea. It's a 3,000 pound car and it's going 30 miles per hour. Now this second part, that ratio right here, it's really a ratio of lengths. This is the fraction of that momentum that's originally in the E hat 2 direction, or really the minus E hat 2 direction, right? And if you take r divided by r squared plus d squared square root, that fraction ends up being about 11.14%. So we've got 11% of my momentum going in the E hat 2 direction, or minus E hat 2 direction, right? 11% of this 3,000 pound car going 30 miles per hour going in the E hat 2 direction. And what's happening here is we've got a tension in the cable which must convert that momentum to 0 in a very short amount of time. Yes? So again, if you write out numbers, this number right here ends up being minus 1,523 pounds seconds. And you have to add in the integral of this tension. This tension doesn't appear for very long. It appears for a short amount of time. I'm going to approximate this by, let's call it an average tension, times a delta t, a change in time. How much time does it take for that rope become tight? Well, if we go back to the video, when we saw that cable break frame by frame, we saw it get tight in one frame, and we saw it break in the next frame. So it took less than 2 frames in order for this impulse to occur. My side of the video was 30 frames per second. So the breakage occurred in something less than 1/16 of a second. Okay, so probably something quite a bit less than 1/16, but 1/16 is pretty conservative. So my average tension times 1/16 of a second has to equal 1,523 pound seconds. And if you work out the math, that means your average tension, again, this is sort of a back of the envelope calculation, is going to be about 22,000 pounds. Ooh, that's a lot bigger than the 7,000, isn't it? In fact, that's a lot bigger than the 15,000 too, isn't it? No wonder the cable broke. And really, these numbers here are conservative. This is my average tension. The peak tension could be a lot higher than this 22,000 pounds. And we said that this the car went in perhaps maybe 1 or 2 car lengths. So the D would be bigger if I were to incorporate that. So really this 22,000 pounds here is a lowball estimate. It's no wonder why that cable broke. It's because the cable didn't become tight until the car was well into this, what was supposed to be the turn. Yeah, if the cable was tight at the very beginning, I would bet that it would only take 7,000 pounds to turn the car around. But that's not what happened, and that's why the cable broke. The end.